Here is our workshop setup again. The drill press is on the left. You can't see it except for the very base of it, but you can see the watt meter. The digital multimeters are still there. They're not connected, so we don't need to see them. The outlet strip that the drill press is connected to is here. I've moved the switched capacitor here, and it is connected in parallel with the drill press, simply plugged into the same outlet strip. Let's turn on the drill press. The capacitors are all switched off. Here's the drill press. Real power on the left. On day 5, we were drawing 216 watts. Today it is drawing 190. That's mostly because the voltage varies in this workshop, just like it varies everywhere on the power system. You just don't usually see it. But it's drawing 190 watts today. Our calculations were with 216, so we're going to see a little bit of difference. But we'll do the reactive power calculations using what we took today. So let's write these values down and hope they don't change too much before I actually switch the capacitor in. So I'm going to turn on the main screen, write down the values, and then try to take the other values fairly quickly. So, drill press data taken on day 6. Okay, no capacitance. We'll just say no C. The power, 194 watts. Current, I, magnitude, 2.04. I'll go ahead and write that last digit down. And voltage, 120.7. Now, I'll turn on the shunt capacitor. 120 ohms. What happens? Not much to what we're looking at there. It's possible that the voltage could change, and I'm going to write this value down. Voltage equals 120.8 or 9. So we'll talk about that. I'm going to go ahead and take the rest of the data. Power, 195. And current. Let's take the current. I is equal to 1.69. Okay, let's talk about these for a moment and do some calculations. So I'll turn off the drill press. Second one is with 120 ohm shunt capacitance connected. So calculations for no capacitance. I have not done these yet because I just took the data. What can I do here? I can say power factor. I'm going to use this equation, P over S, apparent power, which is P over VI. So I can do that calculation. And the value is significantly lower than what we calculated last time because the power value changed so much. We get 0.79, and I'm going to assume it's still lagging since it was lagging last time. We'll find out when we connect the shunt capacitance. So with shunt capacitance, 120 ohms, the power factor is now power 195 watts. Okay, is 195 different than 194? Well, yes, of course it is. However, is it significantly different? Is it statistically different? No. the accuracy of the meter. I've never looked it up. I need to because I keep talking about it, but I haven't. But I cannot assume that one of those was actually 194 and the other one was actually 1 watt more. Still, I'm going to use what I measured as the value. How about the voltage, 120.8? Is that significantly different than 120.7? No, I can't assume that the meter is that accurate. There was another significant digit beyond that 0.7 and 0.8, but still, statistically, I would not assume that that's different. There is one thing in favor of it being different. When you improve the power factor, the voltage drop across the wires should decrease. So that 0.7 to 0.8 may actually have happened, but we can't assume that it did. If we were trying to justify putting this capacitor in, it would be hard to do it based on voltage regulation. How about the current? 1.69 amps. Is that different from 2.04? Yes, definitely. We had a significant decrease in the current, so that one we know is there, and that changes the power factor to 0.96. Go away. 0.96. A significant improvement. Is it lagging or leading? Let's turn this demonstration back on and talk about that, because I don't know. And to know for sure, I would need either a more finely variable capacitor or connect the oscilloscope again and see which waveform is lagging or leading. Here's what's happening here. Drill press back on, 120 ohm capacitor connected in shunt. If I add another capacitor to that, I'm going to add the 240 ohm. It's in parallel. That causes the current to increase. It's a very small increase, but it causes it to increase. Turn that one back on, off, turn all of them off. Here's the 240 alone, 1.79. This is a 60 ohm capacitor. I'm back to no capacitance. Turn on the 60 ohm, and I go down to 1.86. So not quite as low as I got before. If I go to the 30, the current increases. At this point, I know that the power factor has gone leading, and we do not want leading power factor any more than we want lagging power factor because of this. It increases the current. So this is the best I can do with the switch capacitors that I have. And this is actually very practical, because if you go to a supplier and say, I need a 120 volt capacitor that will supply exactly 135 VARs, they're going to tell you we don't have that capacitor. We have probably 100 or 150 VARs, and you can choose from those. In practical terms, utilities will charge commercial and industrial customers for low power factor, but low power factor usually starts at 0.9 and below. So we've gotten it to 0.96. We are fine as far as the utility is concerned. We just need to keep it above 0.9. Doesn't really matter if it's leading or lagging. We could figure it out, but we don't need to. So the takeaway from this is do not know lag or lead. We could repeat the calculations that we did up above and estimate whether it's lagging or leading. But again, we have error in all these measurements. So, and we don't have sinusoidal waveforms. So we cannot say for sure on this. I'm saying it doesn't matter. In some cases, it will matter. If it does matter, you have to figure out how to determine if it's leading or lagging.